f and g, then f plus g is also continuous. Or I'll write in this book f plus g, fg, and then f by g, and then maximum of f and g, and then kf. Such type of functions are also continuous functions. After developing the algebra, we have of the continuous function, most of the things have been solved. Like most of the complicated functions, we can solve it by algebra of continuous function, and then we did a result that if f and g are continuous, composition of two continuous function is also continuous. That means f is continuous at x naught and g is continuous at f of x naught. Then the composition makes sense and composition is also continuous function. And then at last we started with the properties of the continuous function. So the first property that we did in the last class is a function is it's called bounded value theorem, or it's maximum minimum theorem. So let f be real valued continuous function on closed and bounded interval ab. So if f is a real valued continuous function on closed and bounded interval ab, then f is bounded, then f is a bounded function, and moreover f attains maximum value as well as minimum value. Maximum and minimum values on AB. Fine. Attains means there should exist pre-image of the maximum and minimum values of the image set fx. So till now, is everything clear? Should I move ahead, or is there any doubt in any of the summary point, or is any doubt in the previous proofs? I have sent the notes. So is there any doubt regarding the proof of anything? If you have any doubt, you can ask me right now. Because later on things will become more complicated. So should I move ahead?
Yes, ma'am.
Today we'll start with another important property of the continuous function. So first of all, let's spend 2 minutes on this fifth property. So later on, in the last part, we realized that if we have a continuous function on closed and bounded interval, so here closed as well as bounded, both are necessary conditions. Like if if one of the condition is not there, then we cannot say f is bounded. We have closed as well as bounded interval. That's why closed and bounded interval. This will imply f is bounded. So if you remove one of the property, if you just remove one of the property, then it will not happen to be bounded. Like it can be bounded or it cannot be bounded. You cannot say anything. And same thing for maximum and minimum also. For attaining maximum and minimum value, you required closed and bounded in property and plus continuous function. Okay, these three things are required. Bounded means bounded above as well as bounded below. It's a bounded set, right? Or an interval means it is should be of the form this thing. So you need closed bounded interval. So is it fine?
Yes.
Ma'am,
Yes.
here
Yes,
bounded
Nikita.
means that the image set is that is bounded. F is bounded means image set is bounded.
Yes, image set. This set f of x, where x belongs to AB. This set is bounded.
Okay.
This set has to be a bounded set. That means if you will draw the graph of the function, it should start and end somewhere. It cannot be like going to infinity or either from right or from left. Okay? It should start and end somewhere. This graph cannot be unbounded. It cannot be of this form. The continuous function is intermediate to one of the important property of value theorem. So as the name suggests, intermediate value theorem. So that means whatever the value is in between, it should be attained. So as the name signifies, the statement of the theorem says that if you have a continuous function, if f is a continuous real valued function, so if f is continuous real valued function on I, then f has intermediate value property on I. What does that property means? Intermediate value property means whenever you take 2 points in the interval, so whenever you take 2 points in the interval and there is a point which lies between f of a and f of b, then this point should be attained. Should be attained means there should exist some pre-image of this point. Fine, if you take any 2 points a and b belonging to the interval I, then there exists x belonging to your interval that f of x, sorry, f of x is equal to 1. This is the meaning of intermediate value property. That means whatever the value which is lying between f of a and f of b, all of them should have pre-images. So by graph, it means suppose this is your a, this is your b, and this is your functional value f of a, and suppose this is your functional value f of b. So now this intermediate value property says that if f is a continuous function, then everything which is lying between a and b, suppose this is So suppose this is a point which lies between everything which lies between f of a and f of b, it should have some pre-image. Okay, that means if you so then it should have some pre-image here. There should exist some x such that whose functional value is f of y. That means if you have a continuous function and if you take any point lying between a and f of a and f of b, there should have pre-image. Okay, so suppose this is your curve. This is your continuous function on closed and bounded interval. Suppose this is your a and this is your b. Fine. So now this is your f of a and this is your f of b. So what does the theorem says? The theorem says whatever point you choose between f of a and f of b. Suppose I choose this point. So then it should have some pre-image. Fine. So this has a pre-image. At least no, not two. It will just have one because f of b is above. So there
Ma'am,
exists
here
a point, this x, which will become pre-image of your y. Yes, Nikita?
Ma'am, here the x has to belong to the interval a comma b and not the origin like I.
Yeah, I is your AB. Function I means AB. That means the interval on which function is defined is AB. Here, if I'm writing I or AB, that means the same thing. Fine. So there should exist some point between AB such that the image of that point is the point you have chosen between f of a and f of b. That is the really good property of your continuous function. Why? Because function is continuous, so it cannot leave any value between your f of a and f of b. It has to give some value to each and every point. Otherwise, if there's a gap, it will not be a continuous function. Fine. Whatever function you will construct, suppose your function is very bad looking function. Suppose this is your continuous function. Fine. This is your a, this is your b. So now this is your value f of a, and suppose this is your value f of b. Fine. Now if you choose any point between f of a and f of b, suppose this point, it should have some pre-image. Otherwise, it will not be a continuous function. Because see, it should have some point, say this point, right? Whose pre-image is this y. Otherwise, it cannot reach from a to b with a break.
Can this y be equal to fb or fa?
Can this y be equal to?
F
No.
is-
No,
Why not?
it's proper. Why not? See. Oh, can this y be equal to f of a and f of b? then it doesn't make sense, right? Because if y is equal to f of a, that means it already has a pre-image a. So then what we are like looking for,
Okay, okay. Yes.
right? If y is equal to f of a or f of b, that means already pre-images exist, right? So then that means we are looking for nothing. Already we are given that pre-image exists. So basically we are looking at the points which strictly lies between f of a and f of b, such that whether those points have pre-images or not. So it means that each and every point, like this interval, each and every point of this interval will always have pre-image. Fine. So what does you conclude by this theorem? So is there any immediate observation after reading the statement of this theorem? See, earlier theorem was every continuous function image is always bounded on closed and bounded interval, image will be bounded. And now we are saying that each and every point of the uh, each and every point lying between f of a and f of b is attainable. So what does that mean? Combine these two statements, what does this mean? What should image be look like? Image of this
Can you
function.
repeat?
So the question is, after having this theorem fifth and this theorem, like joining the statement of these two theorems, what can we conclude? How does image of the function, continuous function on closed and bounded interval look like? Like these two theorems are very powerful statements and they are giving very nice result. I just want to know that result from you. That if you can see the result or not without, I'll explain to you. Like if you can conclude something. I really want to see if anyone is having that observation far.
Maybe the function is a surjective function
No, function is not subjective.
because it is the okay, okay. If the yes, yes, if the codomain is not this interval, then it will not be okay.
Function is not subjective. Function is from uh, like function is from AB to R. What about image set? Image should look like, how does this set look like? It's a bounded set and it attains each and every value of the endpoint. What does that mean? Isn't it the property of intervals that this image set should be a closed interval? It should be of this form. It's a bounded set, and whatever two points you are choosing, it attains each and every value between these 2 points and also these 2 points. It should be a closed interval, right? Can you observe this thing from these two statements that image of any continuous function from AB to R should always be of this form, interval form, CD, right?
Um, then if this image is of the form CD, then this is just from the first theorem that we did. What is the need of the second, this intermediate value theorem? We can just say that the image is bounded from the first one.
Image is bounded from the.
First theorem.
So no. See, first theorem. First theorem says that image is f is bounded. Okay, image is bounded, and it attains its maximum as well as minimum. Fine. One second. So not just no. So not just interval. Image is always closed set. It can be of the form union of two intervals, but image is always closed. Okay, so let's drop it because I uh, really don't want to like explain you what is a closed set, what is an open set, because it has some definition like proper topological definition, closed set and open set. Like some of the things can be dropped. See, but the thing is, first theorem will not conclude such a statement. Why? Because first theorem just says that the image set is a bounded set. Okay, the image set is bounded, but it can be of this form, right? CD union EF, right? It's all. This is also a bounded set, right? Fine, Atul. First theorem is not saying that it's an interval.
Yes. Okay.
You need something more, and it just says that it attains the maximum and minimum value. But why each and every value lying between maximum and minimum should be attained? That is the question, right? Why each and every value lying between them should be attained? So first theorem will not imply this thing. Fine, but still you need more. Like still you need more stuff to prove that the image is just of this form. Like these two theorems are not sufficient to prove this thing right now. Still you need more theory to develop. Fine. You can see this result. This result is true that image of f is of closed and bounded interval, but still you need more theory. Later on, when if you'll get a chance to study topology on this real spaces, then you will see that every continuous function maps adds connected set to a connected set. So that's why just leave it for it. These two theorems just imply that image is bounded and each and every value lying between f of a and f of b will be attained. Fine. So the theorem says if you have any value lying between f of a and f of b, it should be attained. It should have some pre-image. Is the statement clear? Should I start the proof?
Yes, it is clear.
Still, you need more theory to conclude this result. It's not directly happening from these two theorems. But I have like said you like I have said this result, so that's why I just wrote it. Okay, so what you want to do here is now you want to prove that if you choose any point between f of a and f of b, it should have pre-image. Okay, and f is given to be a continuous function. F is a function from ab to r, and you are given that y is lying from f of a to f of b. Fine. Now you want to prove that there should exist some pre-image such that f of x is equal to y. That means each and every value between f of a and f of b is attained. Function cannot miss any value. Function has to pass from each and every value between f of a and f of b if it is a continuous function. Continuous property is required. Fine. So let's just start with S. So let's introduce a set S such that all those points of A, B such that f of x is less than y. Okay, we can construct such a set right. I'm collecting all those points in this interval whose image value should be less than y. So now is the set empty or non-empty? It should have at least one value. Then it makes sense to talk about this set. So I'm saying S is non-empty set. You have to tell me one candidate for the set. Why it is non-empty?
F of A will always belong to the set.
Yes. So A belongs to this set, not f of A. A belongs to this set S because f of A is less than y. Image of A is less than y. So this set is non-empty. So if it is a non-empty set, then every non-empty bounded set, this set is also bounded, right? Because x can lie from A to B. So it's a bounded set because it's a subset of AB. So it's a bounded set. And every non-empty bounded set has a supremum. So supremum of S exists. Fine. So let's take x naught to be the supremum of this set S. Fine. So now So if x naught is the supremum of this set, then the same argument that we did yesterday, for each n belongs to n, consider such points. Right? For each n belongs to n, if you consider such points x naught minus 1, x naught minus half, x naught minus 1 by 3, all such points will have at least one point between them, y1, y2, y3 from the set, because it's a supremum of the set. So this way you can create a sequence, right? Yn. So for each n, there exists yn belongs to S such that x naught minus 1 by n is less than yn is less than x naught. So now what about the limit of yn? Same argument that we did in the last theorem yesterday. The limit of yn will be what should be the limit of yn?
X naught.
Yes. Apply squeeze theorem. So you have this converges to x naught, this converges to x naught. So yn should converge to x naught. So now you got a convergent sequence which converges to your point x naught, which is a supremum. Fine. Now, since since all these yns belongs to your set S, right? All these yns belongs to your set S, right? So your f of yn should be less than y. Fine, by the condition you have on S. So f of yn should be less than y. So if f of yn is less than y, taking limit both the sides, because this is a constant sequence, limit exists, and here also this limit should exist. Because yn converges to x naught, so f of yn should converge to f of x naught, right? F is a continuous function. So therefore, limit of f of yn should be less than equal to y, which is f of x naught is less than equal to y. So you got f of x naught is less than equal to y. Now you'll try to prove that it is actually equal to y. It's not less than equal to y, it is actually equal to y. Why? Because you want to provide and so your main task is to provide pre-image to y. And you just got a candidate x naught. See, this is your point y, and then you took a sequence, since it's a supremum, so you constructed a set, all those points which are less than y, okay? So these are all those points which are less than y, and now you are taking a supremum. So if you are taking a supremum whose like image value should be less than y, that means you are really creating a sequence that should, the graph should be like this. This is your x-axis, this is your y. So this is your f of a, and this is your suppose f of b, and y is, and this is your curve. And now this is A, this is B. So now what you are doing is you are taking all those x whose image value is less than y. That means all the points from here to here. All the points from here to here, because all these functional values are less than y. So you are taking this set and now you want to prove that whatever is the supremum of this set, that should be the candidate for the pre-image of y. Is it now make sense what we are doing in the proof? So you have taken this set to be S, and now you are proving that the supremum of the set is actually supremum of the set is actually your candidate for the pre-image. So right now you just have proved that this functional value will be less than equal to y, but actually you want to prove that f of x naught is equal to y. Fine, this is your main task. So now how will you prove that y is less than equal to f of x naught? How will you prove that y is less than equal to f of x naught? The same way that you did here, right? Now you will construct a set here. Not a set, like there's some other manipulation, but you'll also try to invoke the same argument that will create some sequence. But here, this time you'll create some sequence as x naught plus something, and you'll apply the squeeze lemma again. So now consider x naught plus 1 by n and let your sequence Tn to be minimum of b and x naught plus 1 by n. So if you choose your Tn to be b, minimum of these elements, like T1 is a minimum of b and x naught plus 1, T2 is a minimum of b and x naught plus half, in such a way, then your x naught always lies less than equal to Tn and is strictly less than. Is this point clear? Why Tn is lying from x naught to x naught plus 1 by n? See, Tn is the minimum value of these two, so it has to be less than x naught plus 1 by n, right? Minimum is always less than the parts that you are taking in the set. And minimum will be either b or x naught plus 1 by n. And your x naught was lying in this interval, right? So x naught, and this is either the minimum is b or x naught plus 1 by n. So it will be greater than x naught. Is this point clear, or do I need to explain it again?
Can you explain
It's a
that?
crucial point. See, we are considering this sequence x naught plus 1 by n. Fine, we are considering this sequence x naught plus 1 by n, and now we are constructing a new sequence which lies between x naught and x naught plus 1 by n, which is the minimum of x naught plus 1 by n. See, this is your point x naught, and now you are considering x naught plus 1, x naught plus half, so on. Like you are reaching x naught from this side. So, what is Tn? Tn is the minimum of b and the value x naught plus 1 by n. That means you are creating a sequence which lies between x naught and x naught plus 1 by n. Tn will be less than x naught plus 1 by n because it's a minimum value. And why it is greater than x naught? Because either the minimum will be b or x naught plus 1 by n. X naught is less than x naught plus 1 by n, right? Strictly less than. And x naught is also less than b because x naught lies between a and b. B is an upper bound of this set and x naught is the supremum of this set. So x naught is less than equal to b. So if it is less than both b and x naught plus 1 by n, it should be less than each and every value of the minimum, right? Because minimum is either this or this. So then your sequence lies between x naught and x naught plus 1 by n. So now by squeeze lemma, you have this converges to x naught, this converges to x naught. So Tn should converge to x naught. So if Tn converges to x naught, f of Tn should converge to f of x naught, right? Because f is continuous. Okay, so till what point? I got disconnected. Is my
That-
voice or
Till that
screen?
Tn belongs to AB thing. After that, it got cut.
Okay, so Tn belongs to AB, but Tn does not belongs to S. Why Tn does not belongs to S? Because this is your set X, this is your set S, and X0 is a supremum, and all the Tn's are bigger than X0 by this thing. All the Tn's are bigger than X0. That means all of them are upper bound of the set. So they cannot be in the set, right? So Tn's are not belonging to S. Is it clear? Is this point? Why Tn's does not belong to the set S?
Yes.
So if Tn does not belongs to set S, that means if it is not in this set, that means everything is bigger than Y. Right? Everything is bigger than Y. That means Y is less than equal to Tn because they are not in the set S. So everything like f of Tn is bigger than Y. Right? If it is less, otherwise the elements has to be in the set. So everything is bigger than Y, and if everything is bigger than Y, taking limit you have f of x0 is bigger than Y, and earlier you have f of x0 is less than Y, right? First equation. And now you have f of x0 is bigger than Y, so your f of x0 should be equal to Y. Is the proof clear, or should I need to explain it again? Like summarize it again? What is the idea of the proof? How each and every value is attainable between f of A and f of B? Anyone please respond? Is there anyone who didn't understand what is going on in this proof?
Ma'am, can you just summarize it once, please?
Okay, so basically what happens in this proof, this is your function, suppose A and B. This is your functional value f of A, this is your functional value f of B. And now what you did is you choose a point between this, and now you want to get a pre-image of this point. So by graph it is clearly visible this should be the pre-image, but now you really have to write down the proof for it that this should be the pre-image. So now what you did is you started with a set S, all those points of AB such that f of x should be less than Y. So what are all these points? All these points, all the elements of S is such points. Fine. You created this set S such that each and every functional value is less than Y, right? So now this is your set S. And now you took the supremum because it's a bounded set. Bounded above by Y, right? Like, no, not Y. All the elements are lies in AB. So it's a bounded set. So supremum of S exists. Right? This is what you can see in the picture, right? The supremum should be the candidate for your pre-image. The supremum of S exists, and you took your supremum of S to be x0. Now what happens is you create, since it's a supremum, x0 minus 1 upon n there always exists a sequence between all these points for each n. And now this converges to x naught, this converges to x naught, so this should also converge to x naught. And these are the points of your set S. That means each and every yn, f of yn is less than y. So their limit value, now if yn converges to x naught, f of yn converges to f of x naught. So your f of x naught is less than equal to y. Fine. Now you want to prove that y is less than f of x naught. So what you are doing is you are creating a set, new set, not set, you are creating a sequence. So you are creating a sequence, let Tn be minimum of x naught plus 1 by n and b. Fine. So you created a sequence from this side because you have already used this side. Now you want to create a sequence from this side coming to x naught. Fine. So you created the sequence t1, t2, so on, coming to x naught, like whatever is the minimum value. If the since the minimum is b, so all the points are b, and then you created this sequence. So now all the points of this sequence lies between, right? All the points of this sequence lies between x naught and x naught plus 1 by n because Tn is the minimum. So this converges to x naught, this converges to x naught, so this should also converge to x naught. So Tn converges to x naught, continuity, f of Tn should converge to f of x naught, and each of Tn belongs to AB, right? All these points belongs to your set AB, but Tn does not belongs to your set S, right? Because this set S is this set. Your set S is this set, and now you are creating sequence here. So it does not belongs to your S because each of them is an upper bound. So if it does not belongs to S, that means each of Tn functional value is greater than equal to y. And if it is greater than equal to y, limit should also be greater than equal to y. And what is the limit? F of x naught. So earlier you got f of x naught is less than y, and now you got f of x naught is greater than equal to y. So your f of x naught should be equal to y. The main thing that you used here is that you are making use of this side, creating a set, making use of the property of supremum, and proved that supremum is x naught, and then you are making use of this side and then proved that f of x naught is actually equal to y. Fine. Is the proof clear? This is a summary of the whole proof, and this is a really important theorem called intermediate value theorem, that each and every value between your f of a and f of b will always have pre-image. You cannot skip any value if your function is continuous function on closed and bounded interval AB. It has a lot of applications. This intermediate value theorem, whenever you will give any national level exam, national level entrance exam, most of the questions are just the applications of this maximum minimum theorem or intermediate value theorem. You just have to apply this theorem, make proper use of it. So right now I'll just give you two of the applications of this theorem. So is the statement of the theorem is clear? At least the statement, not the proof. At least the statement that any value lying between f of a and f of b will always have pre-image. The function cannot skip any value because it's a continuous function. and that should pretty natural occur, right? That should this not the proof is pretty natural. The proof requires a technique, but at least people can think of the statement, right? If it is a continuous function, that means there should not be any break in between, right? This is what this theorem is saying, that you will not have any break between f of a and f of b because the function is continuous. But here also, the important point is it is on closed and bounded interval. Fine. If the function is not on closed and bounded interval, then you cannot say such a thing, that it will not leave any value in between. Fine. If someone wants, you can give me some counter example where the function is not closed, or where the interval is not closed or interval is not bounded and function is skipping some value. You can think of such examples and discuss with me. Okay, so let's see some examples, some of the applications of this theorem. Suppose f is continuous function from 0 1, it's a closed and bounded interval, to 0 1. Then f has a fixed point. Okay, so what does this example says? This is one of the application of your intermediate value theorem. It says if f is a function from 0 1 to 0 1, then there is some x between 0 and 1 such that f of x is x. Okay, this is called fixed point. So first I'll give you the definition. What is the meaning of fixed point? Fixed point means if f is any function from D to C, x belongs to D is a fixed point if f of x is same as x. Fine. D to D, make it D to D, because then you don't know whether x belongs to C or not. Fine. So x is said to be a fixed point if the image of x is x. That means this point is fixed. Function is not changing this value, not doing anything to this point. So now it's a one-line proof. Can someone think of a proof by using intermediate value theorem? Just small manipulation is required. How can I prove that there exists some point such that f of x is x? Any idea? Like, what should I start off? It's just a two-line proof. Direct application of this intermediate value theorem. Okay, so let's just start with a function g from 0 1 to 0 1. such that g of x is fx minus x. No, not this is not a function from 0 1 to 0 1. Let's forget about domain and range, but at least the domain and range will be like domain will be closed and bounded interval.
Like after this, we can say that there is some x for which g of x is equal to 0.
Yes, at least g is the domain will be minus 1 to 1, right? Closed and bounded, right? So if it is closed and bounded, and by algebra of function, it's a continuous function. And now, Rajneel, what you are doing?
Yeah, like we can say that there is some x for which g of x is equal to 0 by IV.
But what functional value should I take? Sorry, domain will be again 0 to 1 because values of the x is always 0 to 1. Codomain can be minus 1 to 1. So now your g of 0 is f of 0 and g of 1 is what is f of 0? F of 0, f is a function from 0 1 to 0 1. That means it is greater than equal to 0. And f of 1 can be at max 1. That means this is less than equal to 0, right? At max it can be 1. So now your g of 1 is less than equal to 0 is less than equal to g of 0. Now what happens? How will you apply intermediate value theorem? You got a point lying between two functional values. So then by intermediate value theorem, there exists a point in 0 1 such that g of x is 0, right? Which means f of x is the proof clear? Whatever you want in the proof, you constructed that function in such a way that you can apply intermediate value theorem. So then you got that every function, every continuous function from 0 1 to 0 1 always has some fixed point. If your function is from 0 1 to 0 1, continuous function, any continuous function, any bad looking function you can create, but the range should be 0 1. So it's any it always have a fixed point, like it always intersect with this line. Okay, it will always intersect with this line at least once. Is the meaning clear what we are doing in this example? That any bad looking function that you create from 0 1 to 0 1, it will always intersect this y equal to x line. And there's also a partial converse of this intermediate value theorem. Like the converse is not true, that uh, if any value which is lying between f of a and f of b, if it attains a pre-image, we cannot say that f is continuous. The converse is not true, but the partial converse is true. Partial converse means putting some of more restrictions, then the converse is true. Okay, so in the next class, we'll look at the partial converse of this theorem, intermediate value theorem. And then after doing that partial converse, we'll look at the questions. So next class, we'll try to solve the problems. Like after spending half an hour on the partial converse, then we'll try to solve more questions. And meanwhile, just try to look at this example, that if you have any positive number and m belongs to n, then y has positive mth root. Or maybe this is also one of the applications of your intermediate value. Meanwhile, you can try out this thing, that if f is continuous function, if f is continuous function on an interval I, then image of f of I is also an interval, or a single point. Fine. So this exercise says that if you have any continuous function from any interval, continuous function on closed and bounded interval, this is your interval, I is closed and bounded, then image of this closed and bounded interval f of ab is either an interval, any interval. So there are 4 types of intervals. So it's either an interval or a single point x naught. Image is either a single point like constant function, or image is either a uncountable set like it's an interval. So who wants to try this question for the next class? So it's a proof. The proof of this question is an exact corollary of the intermediate value theorem, which is given in the book. It has been proved. So who wants to try for that? Someone please initiate for this proof. That image of closed and bounded interval is always an interval or a single point. You just have to make use of intermediate value theorem and the last theorem. The image is bounded and maximum and minimum is attained. Look at the proof in the book. Write down the proof, send it to me. I'll let you know whether your proof is correct or not. Who wants to volunteer for this? Nahida? Nahida, are you there? So can you just present this proof in the next class? Fine? Yeah. Good. Gurneet will present her proof. Yeah. So, Tarini,
Yes.
screen is not visible.
No.
So when does the screen sharing, like, have you seen the problem, right? The problem that I have given for the next class.
Yes. Yes.
Okay. So this is your proof.
Yes. Okay.
Maybe I'll
Shall I start? Okay.
one second. One second.
We had to do 1 upon n log n raised to p, show that it converges if and only if p is greater than 1. And to do this by integral test, we have to show that this limit exists. So obviously there will be 3 cases where p is less than 1, p is equal to 1, and p is greater than 1. So first we start with p is less than 1. Ma'am, can you scroll a little bit?
Yeah. Just one second. Maybe I'll download it so that I can also write it there. Because some people may get lost. Fine.
Okay, so the first case is where p is less than 1, and we have the same limit of the integral. And the way we can solve this is by actually substituting some like random variable t. And if we take the derivative of t, we'll get dt is equal to dn by n, which is useful because if we can see the original integral, that's what's remaining outside the log n part. So when we substitute t in the original integral, we get 1 upon t raised to p dt. When we solve that integration, we get t raised to 1 minus p upon 1 minus p in the limit integral test. And so because p is less than 1, the log part stays in the numerator. And here we are substituting back the value of t. So when we take the integral limits, we will get the log b part and the log 2 part that we can see on the screen. As b, it will also tend to infinity, and since that part is in the numerator, that limit will not exist, as in it will diverge to infinity.
So
And
here-
so from
Here we are using that p is less than 1. So that's why this part will be in the numerator, and then limit tends to infinity. So limit does not exist. So by integral test, this series is divergent.
yes, and we use
Fine,
a similar
go
thing in the case of p equal to 1 using the same substitution. We just don't get that 1 minus p as the power, it's just directly the log. And we know that integral of 1 by t dt will be log t. And so again, the log of log 2, the limit exists, but the limit will not exist for the log of log p part. Again, it will diverge, and so by integral test, the series will also diverge for p is equal to 1. The different case is when p is greater than 1, where again we're using the same substitution, but here because we have the t raised to 1 by p, 1 minus p, but since p is greater than 1, 1 minus p will be negative, so we can take that term to the denominator. When we do that, we will get, like, again, we substitute t is equal to in the denominator. And since log b will diverge to infinity, 1 upon log b will obviously converge to 0. And therefore, that limit exists. The limit of this integral exists. And so by integral test, the series will converge. And then the second question, we sort of use a similar strategy where we take a substitution, t is equal to log of log n. When we take the derivative of that, again we can substitute the rest of the integral terms as 1 by n log n dn. So the whole thing becomes 1 by t dt. And the integral of that is log t. So we get log of log n. And here log of log 4 will obviously, the limit exists. So the only part we need to worry about is log of b. And since log b will diverge to infinity when b diverges to infinity, by integral test, the series will also diverge.
Yes. Fine. Everyone understood what she has written the proof. So here in both of the questions, you just need to apply the integral test. So that's why your integral test is so important, because you cannot really solve this by comparison test or by your ratio test or root test. You really need your integral test. So thank you, Dharini, for solving these big problems.
Thank you.
Okay, so next is Gurneet. So last time I introduced the Dirichlet function, and I told you that the Dirichlet function is not continuous at any point of time. It is always a discontinuous function. So let's see, she has written a proof for that it is always a discontinuous function. One second, we can't scroll it up and down. Fine. So, Gurneet. Yes. Start presenting your argument. What you have written here. Everyone can see the argument, right?
Yes.
Yes.
So in this question, we was given a function whose output is 1 when we take it as a rational number, and if we consider x as a rational number, the
Punit, your
this
voice
function
is
is
breaking. So yes, yes.
which converges to x naught. For example, by equal to x naught plus root 3 by n. So by definition of limits we can prove that this limit converges to x naught. Then according to sequence criteria definition, if a function is carried to the continuity, if for every sequence xn which converges to x naught, f of xn also converges to x naught. So here f of y1, f of y2, y3, they all are equal to 0 because f of y1, y2 all are irrational numbers. Therefore, f of yn is constant sequence with entries 0, 0, 0. Therefore, f of yn converges to 0. But f of x naught is equal to 1 because x naught is an irrational number. X naught is a rational number. So this implies that f of yn does not converge to f of x naught. This is a contradiction to our assumption. Therefore, f is not a continuous function, or f is a discontinuous function for real.
Okay. Thank you, Punit. Maybe I'll explain it again because your voice was breaking in between. Thank you so much. So, what we did is we have the function, this Dirichlet function, and then we assumed that suppose your point at which you are checking whether the function is continuous or not, you are taking supposed to be rational number. So now you can create this sequence x naught plus root 3 by n square. Since x naught is rational and n square is rational and you are putting root 3, so it's an irrational number. So now your sequence is an irrational sequence converging to a rational number. So every image value should be 0 because the function is 0 on every irrational. So f of yn is 0 for all n. But x naught is rational. So f of x naught should be 1. So a constant sequence 0 should converge to 0. But here f of yn is not converging to f of x naught, which is 1. Therefore f is not continuous. And similarly, if your x naught is irrational, then you can create a sequence of rational numbers, because you know that if you have any real number, how to create a sequence of rationals in your sequence chapter. How you can create a sequence of rational converging to your any real number. So then you create a sequence of rational converging to your any real number irrational, same argument will be applied. There you will have a constant sequence 1 converging to 1, but the value of the function is 0. So f is discontinuous at each rational as well as irrational. Therefore, f is discontinuous everywhere. So is the argument clear, or is there any doubt in this argument? Why this function is discontinuous at each and every point of R?
Ma'am, I also tried to do this question by the epsilon delta definition. So, like, I got confused after a few steps. So, can you like give an idea of how to do it by the epsilon delta definition?
By epsilon delta definition?
Yes.
Like, I really have to first try it out. I don't think epsilon delta definition, like the proof is easy with the help of epsilon delta definition. I don't think proof is easy with the help of epsilon delta definition. Because that's why you have these two criteria. If we cannot derive something from epsilon delta, then
Okay.
Because see, when you apply your epsilon delta definition, then you have f of x minus f of x naught, right? So then you have f of x, suppose your x naught is rational. So f of x minus 1. Fine. F of x minus 1, you want to prove it to be less than epsilon.
Yes, so f of x minus 1 is less
But
than
f of
epsilon.
x can be anything, right? How will you prove that it will be less than epsilon whenever your x? How will you find that delta?
It's like, can we not say that since f of x minus 1 is less than epsilon, then
So
x has to be a rational number, and then since
x has to be a rational number. So basically your epsilon, so f of x is lying between 1 minus epsilon and 1 plus epsilon.
yes, but since there are only two functional values, 1 and 0, it f of x can only be 1.
1 second. So you have 1 minus epsilon and then 1 plus epsilon.
Yes.
So functional value can be either 0 or 1.
But it cannot be 0 because if we choose any epsilon less than 1, it cannot be 0.
Okay, so you can choose your epsilon to be close to 1,
Yes,
close to 0.
close
So
to 0.
then your functional value is 1.
And then since the functional value is 1,
Your x is rational.
rational, yes,
And your x naught that you have chosen is also?
rational.
Yeah, but then how will you find that delta? Like there are infinitely many rational points,
Yes,
right?
this is the point where I got stuck.
Yeah, because how do you know when their distance is close? How the distance should be how much the distance should be close enough to get that f of x minus f of either. So then this, I guess this is the way of doing it, like convenient way. If you go by epsilon delta definition, maybe I'll think about that argument. I'll write it down somewhere and then send it to you.
Okay, thank you.
Fine? Okay, so one last thing is this online class okay, or do you want something else? Because the strength is pretty much less than the last class. Last class there were, I guess, 30 to 40 students, but today I just have 21 to 22 students. So is there any problem with this online class? If you can convey the views of your friends who are not coming, is there any problem with that? So no one knows anything.
For me, it's okay. I don't know about other people.
What about Jishnu, Tarini?
Ma'am, it's
Yes,
fine
the
with me.
class is okay.
Yes?
Yes, it is okay only.
Okay. So Amitesh, Aratrik, is it fine?
Yes, ma'am. It's fine.
Yes, sir.
Okay.
Fine.
So then let's see when I'll come back to campus. So when you are having your next midsem?
4, 5, 6.
Like second week of
Second week
July.
of July. Yeah, then fine.
No, first week of July.
Yeah, sorry. It's 4th, 5th, 6th are the days. Sorry.
So then you really have to tell me what sir is covering for you so that I can prepare accordingly. Like I'll communicate with Atul. Maybe Atul, are you attending classes or not?
I don't attend all the classes.
So who is the one who used to attend all the classes? Is there anyone who is attending all the classes? No one attend all the classes.
Ma'am,